In the previous video, we saw why deep neural networks struggle to train as they get very deep, a problem known as vanishing gradients. See, identifying the problem though is only half the story. Okay? In this video, we're going to focus on the actual solutions, the architectural ideas that made very deep neural networks trainable in practice. See, these ideas are not just theoretical. They are the reason modern deep networks can actually scale to hundreds or even thousands of layers. Let's now see how vanishing gradients problem is actually solved. Let's jump in. So what are we going to do about this vanishing gradients? Well, there are a couple of techniques that we can implement which will help with this vanishing gradient problem. The first one would be something called residual connections. So what are these residual connections? A simple schematic of residual connection looks like this. So again, you have a layer here. Let's just think of this as a block of layers, as a single layer, like a convolutional layer. Okay. So you're giving it some input, some output is going to come out of it, right? What we are saying is the assumption is, see this layer, whether it's a single layer or block of layers, they're introducing some noise, right? And the more and more layers are chained on top of each other, the noise grows and it overwhelms the gradient information. So what we're saying is this layer is introducing some noise. Why don't we just take this original input and add it back to the output coming out of this layer? That's the trick residual connection employs. So it takes the input and it adds back to the output coming out of the whatever the layer that is introducing the noise. That's called a residual connection. It's a very simple idea. Okay, but in practice, it has been observed that introducing this kind of a residual connections, where after each layer or successive layers, where if you are adding back the original input, whatever the input it doesn't have to be the input pixel, the original input pixels, whatever the input you're adding to these layers here, right? If you add this input back to the output, it has been observed that it will help to some extent with the vanishing gradient problem. Okay. So how do you implement this in practice? Let me show you very quickly with some sample Keras code. Okay. If you do not understand, don't worry. We're going to again look at some residual connections in the project, which we're going to do. Okay. So let me quickly show you, how this residual connection might look like. So again, in this table here, I'm just showing you a model and of each layer in a model and the corresponding shape for that layer of coming out of that layer. So first one is just inputs. Inputs is keras.input, right? So let's say we have an input image of 32 by 32 pixel and 3 is the depth, RGB, right? Red, green, blue, 3 channels. So what is the shape of the input layer? It's just 32 by 32 by 3. Okay. Now let's say we add a convolutional layer on top of this inputs. Okay. So we say layers.conv2d, then we say, and let's say we want 32 filters in that convolutional layer. The kernel size is 3 by 3. Okay. Activation is ReLU. We are calling this, right? Chaining this to the inputs. Okay. And again, we're going to call this X. So what is the output of this convolutional layer, this 2D convolutional layer? The output would be, for example, remember I have given in a previous video the formula to calculate the output shift, but basically it's like 32 minus 3 is 29 plus 130. The stride is 1, right? Because I have not chosen any stride, means default is 1. So 32 minus 3, 29 plus 1 is 30. So 30 comma 30, and you have 32 filters, so the depth would be 32. Okay. We haven't done any residual connection yet. It's just like, we applied a convolutional layer to the inputs. Then, let's say we have another convolutional layer we want to add with 64 filters. But before we do that, let's say this second convolutional layer with 64 filters, let's say this introduces some noise. So for that, what we're going to do is we're going to do a residual connection. What that means is, before you introduce the second convolutional layer, before that, what you do is store this X. See, this X is going to be as an input to the second convolutional layer. So just store this X into a variable called residual. Just put it aside, So take this X and put it into, save it as a residual. So this residual shape is same, right? 30 comma 30 comma 32. So we're keeping it aside. Okay. So now what we do is, so we want to add, right? So let's look at the output of this second convolutional layer. Okay. So the output of the second convolutional layer, what would that be? So you take this X as your input, right? And on top of that, you're building the second convolutional layer. Okay, padding equal to same. If padding equal to same, whatever the input, you pretty much get the same, because stride, there is no stride as well. So padding equal to same, you're going to get pretty much the same shape. So you started with 30 comma 30 comma 32, which is your X. So if you apply a 2D convolution layer with 64 filters, the output would be 30 comma 30, but now the depth would be 64. Okay, so this is the output of the second convolution layer. Okay, so we want to add the residual to this guy. So what is the shape of the residual? 30 comma 30 comma 32. Okay, you want to add this to 30 comma 30 comma 64, but if you see the depth doesn't match. So because of that, what we do is we do a one by one convolution to the residual to first convert its depth from 32 to 64. So what we do is you take this residual and on top of that you apply this layers.conv2d. So now you're going to use 64 filters, but you're going to use one by one convolution. Okay, so when you use one by one convolution with 64 filters, your residual from 30 comma 30 comma 32, it will become 30 comma 30 comma 64. Okay, great. So now the residual is the same shape as the output of the second convolution layer, which is also 30 comma 30 comma 64. Now you can finally say layers.add this x with residual, and your shape would be now 30 comma 30 comma 64. In essence, you have implemented a residual connection. Okay, so just wanted to show you with some simple Keras code how this residual connection might look like. See, right now in this situation, I haven't used any max pool layer. So if you use a max pool layer, like for example, after the second convolutional layer, I'm using a max pool layer. How would you implement this residual connection? It's pretty much the same, except that, when we are adding, when you're doing this point convolution, like one by one convolution, you use a strides equal to 2, because after the max pool layer, the output shape got downsampled. So you want your residual also to be downsampled. So you use a strides equal to 2 to downsample, and then again you can add them up. Okay, again I will leave it as an exercise so that you can play with these shapes, to make sure that you understand how this residual connection works. If it is not clear, please wait till we do the project, and you can probably double check your calculations again to see it really makes sense, how you add the residual connection. But the intuition or the essence is this: take the input to whatever the layer is producing noise, right? Take that input and add it back to the output. Okay, all right. So now let's talk about another technique called batch normalization. So residual connections definitely helps with vanishing gradient problem, but there is another technique called batch normalization, which also helps with the vanishing gradient problem. So what is this batch normalization? First, we have already seen what normalization is, right? Normalization is nothing but scaling the data. So for example, in the previous videos, like when we built our model by training on the CFAR dataset, we divided our input images X by 255 to basically make the pixel value scale in the range of 0 to 1. That's kind of a normalization. But that's not the only way, right? We could normalize in a different way, where we could subtract our input data X with the mean and divide by the standard deviation, basically centering our data around 0 and with standard deviation of 1. This, of course, assumes that our input data follows a Gaussian, normal distribution. Okay, so this is a way to normalize data. Now, batch normalization does something similar, but in batches. Okay, so what exactly is that? It adaptively normalizes the data even as the mean and variance change during training. And it basically does it by using the mean and variance of each batch during the training process. Okay, so each batch's mean and variance is used to normalize the data in that particular batch. Now for inference, you do it a little bit different, because in inference, again, you could inference with a single sample or a batch of sample. So you use an exponential moving average of the batch-wise mean and variance of the data. So during training, whatever the mean and variance of each batch is computed, right? So it keeps track of an exponential moving average, and it uses that to scale the data, to normalize the data during the inference mode. Okay, so this is just another technique, right, which kind of helps with vanishing gradients problem. Now you may ask why. Why does it help? Well, as to why batch normalization works, it's purely empirical. Now some people may offer some explanation, but again, as Frank Colle, right, the author of Keras, the deep learning Python work, he explicitly mentions that, while many people can offer some explanation, at the end of the day, it works in practice. It has been observed to be empirically good. As with everything in deep learning, right? Most of the things in deep learning, it's not like exact science, right? It's an engineering discipline where you experiment with different things and you have some best practices. So batch normalization is also one of those best practices, which showed to help with vanishing gradients. In fact, some deep neural networks, if you want to train some deep neural networks, by stacking many layers, it won't even train if you don't have a batch normalization layer. Okay, so we talked about two techniques, residual connections and batch normalization, that can help with this vanishing gradient problem. All right, hopefully this video clarified how we deal with the vanishing gradients problem as we build deep neural networks in practice. See, residual connections help the learning signals flow through very deep models, whereas batch normalization keeps the training stable. If this video was helpful, please feel free to like or subscribe so you don't miss the next interesting part or concepts in deep learning. Please stay tuned for more insightful and interesting concepts in deep learning, and happy learning.